Hi everyone, thanks for viewing this video. My name is Chris Wright. I'm a senior engineer at Gavin and Doherty Geosolutions, and together with the Selkie partners, we're developing open source tools to aid marine renewable energy developments. Today I'm going to be talking about the mooring module. The mooring module will be used for the automated initial sizing of mooring systems, both catenary and taut, for wave and tidal energy converters. The mooring system provides a vital element of station keeping the marine renewable energy device within the required offset envelope, meaning the survivability of the dynamic power cable, allowing power produced to be exported to the grid. Here we can see a few images of mooring systems to set the scene. Bottom left, there's Orbital Marine Power's O2 floating tidal energy converter, and top right, the Wello wave energy converter. Inputs to the tool are shown here and include body parameters, environmental conditions, and various design choices the user can make. Mooring design can either follow an automated sizing or a user design space search. In the automated approach, the user does not specify the input line lengths or anchor positions, whereas in the design space search, the user specifies a possible range of values for these parameters. That is min, max, and the step size. For catenary moorings, the automated pre-sizing is taken as in DT Ocean Plus. The line length is computed as a theoretical minimum line length to avoid vertical forces on the anchor point when the tension reaches the value of the minimum breaking load of the line. The anchor radius is then set so that the line pretension equals the variable set by the user. For taut moorings, the line length is set taking into account a seabed angle and required pretension. The tool has a number of basic assumptions. Firstly, the hydrodynamic body is a single rigid body. Analysis is carried out in the frequency domain using a quasi-static mooring analysis with a linearized stiffness curve at the mean offset position. The number of lines should be 2 or more, and all lines are of a uniform line type and are equally spaced. The tool builds on existing open source tools. As well as the previously mentioned DT Ocean and DT Ocean Plus, 2 other simulation methods are used in this development. MoorPy is a quasi-static mooring model developed by NREL in Python. We use it to calculate the equilibrium offset positions, linearized mooring stiffness matrix, and peak mooring line forces at the maximum offset. NEMO is a boundary element method code for the computation of first-order wave loads. Developed by École Centrale de Nantes, the mooring tool has been designed to import user-generated NEMO format hydrodynamic parameters, but also includes the option of 2 default bodies that come supplied with the tool. Design checks include natural periods, mean and dynamic offsets, and peak line tensions. The significant and most probable maximum offsets are calculated following a Rayleigh distribution. If failure in any of the design checks occurs, the catenary mooring system will be modified, firstly by increasing the diameter of chain and then increasing the number of lines. For a taut mooring system, the pretension will be increased while the seabed angle will be modified. Following this, the diameter of the rope will be increased, and finally increase the number of lines. Outputs of the tool will be a table of results, a graphical representation of the design, and a Moordyne input file for further analysis. Now I'll move over to Python, where I'll give a live demo of the Morin tool. Here's the current version of the code. I'd like to note that it's still undergoing further development and testing and not yet in its final format. In this first part of the code, we import a number of standard Python dependencies, as well as MorePy and some Selkie MorePy additions. For environmental conditions, we're looking at a site off the south coast of Wales in water depth of 45 meters. In this demo, we will design a catenary system with a 20% pre-tension using a default large rectangular box hydrodynamic body. Mean and dynamic offsets limits will be 20 and 30 meters respectively, as shown here. I'll run the code now, and we should see a number of iterations as the code progresses through the design checks. In this case, the code should just take a few seconds to finish and produce a design which passes all design checks. Here we can see it took 54 iterations in order for all design checks to pass. Now I'll look at the output results table firstly. Here we can see the number of lines, chain diameter, line length, anchor radius, anchor horizontal and vertical forces, estimated cost of the system, and finally the design checks, where a red 0 indicates failure and a blue 1 indicates pass. As I scroll down, the chain diameter will increase, and as we can see, it was the max offset which was the critical design driver for this example case. In order to pass all checks, we required a chain with a diameter of 152 millimeters and lengths of approximately 160 meters with an anchor radius of approximately 150. The cost of the system was approximately 360,000 euros. Moving to the graphical output of the design, we can see this 3D figure of the final design at the max offset position. So that's it for this quick presentation and demo. More detailed information will soon be published in a report format. If you have any questions, suggestions or comments, please send me an email. You can find my email address on the intro slide. Thanks for listening.